Okay, this is like deep breakdown into this vanilla net. The part actually matters. So this paper mentions some technique, something like a deep training strategy. It's like if we are skipping all the you know like background introductions and stuff like it. If we only look at the essence of this paper, the most important two parts are like a deep training strategy, and another one is like serious informed activation function. With these two techniques, what it can do is if you scroll down, scroll down, scroll down, it can do is like this chart. You can see to achieve the same accuracy with some very famous neural network, it can do it with a lot less depth and a lot less GPU latency. That means like if you are given the same powerful GPU, it can like better leverage this GPU because there are like much less connections and other nonsense operations during forward calculation, and like that means also like much simpler in backward operations. So like it does a lot of experience, like it do image detection with Coco, and even use this GradCam to visualize that its heat area to see what the attention map is focusing on. But all these like they are just doing experiments like to explain why this work, why their like work is like valuable in some area. Like I'm not even very sure like I want to like dive too deep into this part because cam or like grad cam techniques that are easily subject to cherry picking and stuff. Like it's not very demonstrative of how why this thing actually works. But they does bear like very amazing techniques to combine layers. Like I find like this is specific like I said, deep training strategy and this series informed activation function. So let's look at what are they. Look at the code, like what are they. So this notebook is uh, where I borrowed a lot of their code because without like their original repo, it's really hard to reconstruct their study. And you can see they do have something like it's called a series informed activation function. Series informed, per my guess, is that you are not looking at the current pixel. For the next layer, after that activation, we are looking at the activation of all the surrounding area from negative n pixel to the n pixel, comparing to the current the position of current pixel. That's basically meaning you are like this activation is covering 2n+1 kernel size convolution. Of course, this is necessary if you are going to throw away lots of skip connections and you are going to use much less depths of convolutions. You have to use this kind of wide technique to cover huge areas of things. And since if you want to do this, like somewhere in the paper it mentioned, if you want to do this kind of area coverage or something like that, you need to do it in a very fast and parallel way. And the way you're looking at this is like how they covering the area from last layer is basically looks like how convolution works. So they're just using a convolution to do that. So what they do is their SI activation layer is just a way to combine things, and just a way to shift all the area coverage from the last layer. So this is pretty smart. Like they're using something like you combining like they sorry, like let me introduce you to this concept first. So most of the module in VanillaNet, they have two state. They have a training state, and they are using this function called switch to deploy. But I changed the switch to inference. Like I like this word better. So using this switch to inference to switch it into another layer, another state. Like when you're deploy it, or like when it's doing inference, you can use much less weight, which means like much less memory footprint and much less flops calculation. And you can see most of forward functions, it has two states, like if it's inference state or if it's not inference state. Like if you scroll down to its vanilla convolution block, each block will has two states, like simpler states, like much complicated, like two count layer states, if you combine into one, it will occupy like less memory footprint. It's that simple. So during this operation is like you cannot just combine them. Like if you combine lots of things, the calculation result like the same model will output different things. But they figure out a way like before and after calculation, you can do this math operation, which like two of the parameters are from say these two are from like previous convolution layer. Its weights, its bias, and these four, if you're familiar with batch normalization, that's just combining a convolution layer with the following batch normalization layer, which happens a lot in neural network backbones, into one single convolution layer to prepare. It might combine with further with other things, because if it's just a convolution layer, it will be much easier for other combining operation. And you can see these like four things. The ones I mentioned from the parameters from batch normalization. They are just each time you do batch normalization, what you do is you minus the mean divided by standard deviation. This is basically standard deviation, plus the epsilon to prevent all the zero errors. What you have is like you do this operation, then this is like a momentum mechanism, and this is a like gamma and a beta. They're all basically learnable parameters, and with all four parameters, you can do this math operations to keep to keep like the output to be exactly the same. So you can see it's like calculate these new weights and switch it into a new convolution layer. Then it outputs the output is the same thing. So you can try to like run this series informed activation layer, and you put in any activation layer if you like. It's like I change it into to make this code like a more robust to other activation layer. If you want to pass in other layers like sigmoid, if you want, you can do that. But like in the original paper, they only do ReLU so far. So what you do is how do you test it? How do you test that? Like it has two states, like I said, right? So you assume some random x input, and you can see this is y1, this is y2. Like before it switched to inference state, and after it switched to inference state. And notice like before and after, these two are two different neural network structure. Like these has two layers, and this has only one layer. And you can see the forward calculation there. If we compare element wise, the biggest gap is only 2 point something times the power of -7. So it's a pretty small number. Like the two results, they are pretty much the same. So it moves on to a vanilla conf block. What they do is like also like lots of combining. It has a switch to inference. Like this is a switch. Like after you switch, you can combine two weights of convolution into one weight of convolution. Like before you're combining, you have to go through a convolution number one, then liquid value, then convolution number two, and you can output this thing. So after the combining, these steps, like you only have to go through one convolution. That's much less VRAM footprint. That's much less flops calculation. If you compare it here, let's print out shape and number, and this number is basically a parameter number. Sorry, I didn't specify that. Okay, if you try that, you will find we did the same comparison. You can see this is before combining, this is after combining. If you print out parameter numbers layer by layer, weights by weights, you can see this is before, this is after. So the before number is 90k something, the after the after combining the block reduce its size. And for this thing, it's you can see it's only the input side is only 64, right? Yeah, the input size is only 64. Then it moves on to 128. that means like the Cartesian product is much less, right? So for the first part, and after combining, you can see its shrink is not that obvious. But if you're considering most of the combining happens in this paper, in their neural network, is mostly like with the same input size. So that means usually the model can shrink half of the size if you're if you're combining in this way. We can also compare the prediction number. They are pretty much the same, like even a smaller gap than we compared before. So this is like one block. This is one block. So the VanillaNet is by no means small. That they are by no means small model. They are just you can train a very huge network with very wide features, and later on you can combine it into much simpler network. Okay, let's move on to see like how they combine it. Like say okay, convolution is just in some way the linear layer performing very strange operations in like the future moving pattern that you guys familiar with, right? So so what it means is like if you do things like say okay, if you're looking here, if you switch this convolution layer to say linear layer, it still like linear activation linear. This is like if you're looking at this is a very simple stacked convolution or MLP structure. If you're removing this activation, it's basically doing one single linear operation. So like if you're removing this, the neural network will be less powerful, and that's why we are putting activation here to break the linearity, because it won't be one single layer anymore. It will be two layer, which is capable of handling more complex logic. Not like if one weight is strong, like the input will like result in much stronger output. Like they are not direct. Like you have to consider the combination of multiple input elements. So how do they move it? It's quite simple. Like they finally remove this thing. It's like they design a dial. It's like you can slowly dial this thing down. It's like what they says in paper. Something looks like with a lambda. It's like they have this lambda. Like they can slightly dial down this activation function and make it more and more like identity operations. Um, that means like this layer exists during training, and also during the training they will like fade this activation out and to make it like a very wholesome convolution. So once this thing its impact is very minimal, you can just do the matrix multiplication here, like the paper said. You can do the weights of first layer times the multiplied with the weights of second layer. That will be the weights of the combined layer. Like this thing will be like non-linearity. If we draw out the activation, it will be the same layer. Okay. So how they do that is they do it with leaky radio. Like they change the negative slope of leaky radio. So for leaky radio, it's like radio. If you're looking at this, if you are doing this, it's like this is radio, right? Any value you input, north of 0, it will return the original value, like 4 returns 4, 3 returns 3, and anything negative will be bring it up to 0. So this is how the curve look like. Everything north of this original value here all 0. So leaky value is like saying, okay, if you are using value half of the information, if assuming your distribution is pretty average in the middle, you will probably drop half of the information. Of course, this is also the course that you have to do if you want to drop the linearity. But that's why people design the leaky value. It's like you set the leaky like a negative slope to 0.03. It's saying like anything north of 0, you keep it value, and it's anything less than 0, you times it with 0.03. That's like decrease its slope, something like this. And what they do is like they keep changing the slope. They keep changing it. Like during training, when it's here, the non-linearity they still exist, and they keep changing it until it's 1. When it's 1, it's almost like the activation layer doesn't like exist. It's the input is identical to the output. It's almost identity layer. So what they do is change the slope. So let me visualize it here. Like how they do is like if you assume you have a pile of data, this distribution is like random Gaussian data. Random Gaussian distribution looks like a mountain. It's high in the middle, which is 0, and standard deviation is 1. Okay, if you're doing a leaky value, it will look something like this. Like the red one is after the activation, the blue one is before the activation. Okay, if you change it if you change the negative slope to 0, you can see this is basic value. Everything big here, it's still here. Like if it's less than 0, it will be transformed to 0. So that's why you can see a very high 0. But if you slightly turn up the negative slope, you can see it will look something like this. It's still got negative. It's still got like a non-linearity, but it will look something like it because like you times it with a smaller number. The half of amount slightly shift here, and if you're like changing to 1, you can see the before and after activation, they're exactly the same like we suggested here. And that's how they do it. Like that's how they like slightly fade away an activation layer. After they fade away the activation layer, you can see in this block here, in this combining here, this is how they combine things. Like they basically just let's see, like yes, they just basically this is the weight of like second convolution. This is the weight of first convolution. They time it together, and they have the weights for the new convolution, and they throw out the original 2 convolutions. And you can see the size. I've shown you the size before. And imagine you're building the entire neural network with this kind of blocks. That's why how they say like during deployment you can have much quicker neural network. Like you can train with much beefy GPU, but you can inference it with much less GPU. And okay, this is like basically the same. Like when defining each module here, you can see they have switch to inference. They have this like this is just combination happens in stem layer, happens in all the stages, all the blocks, and happens in top layer. And of course, I made some modification that if you don't want to load the top layer, you can. It's like you only load the backbone instead of top layer. If you want to do some transfer learning, you can. That's basically it. You can have neural network. You can have neural network that each step that supports 2 states. You can train it with states, like you can inference in other states. And here is comparison. They would say if you have like before and after switched of state, the before total parameter is something like this, and after is something like this. It's much smaller, both in flops number and in parameters number. But of course, I didn't print out the flops number because that's just too much work for me for single afternoon. Okay, so this is like comparison. You can also see for these 2 entire networks, the prediction, they're pretty much the same again. So they like this is like I guess this is their major invention, but they also mentioned this work somewhere in their paper about some other people's previews. So I guess other people also has done some like work on this front. Okay, so so this paper did a lot of things. This paper did a lot of things like even did this came visualization, which I don't like really dug very deep into it, because like it can be easily cherry pick. It's not like no question to the integrity. It's just I don't know. It's like it's not very convincing how they explain things about like how their features are more something. But I do want to try if they do have a wider feature map. I guess they are pretty good at reconstruction, like content reconstruction. It's like based on the activation output, like you want to say reconstruct the entire image input. So this is my wife eating chicken. Like I don't know how this reconstruction is going to work. So it might be horrible. So it might as well. I'm not using my picture. I'm using her picture. Like she barely checked my GitHub page. That's why it's a very safe place to use her photo. Okay, so we load this VanillaNet 10. You can see from configurations like VanillaNet 10. That's basically this thing, right? It has a lot of layers. You can see lots of dimensions, lots of layers, and you can download. They do offer pre-trained network, so I download the pre-trained network with a progress bar. If you just use my code, you will easily download the model into your local computer and or server. It has two versions. It's like every weight has a simple model version or model EMMA version. EMMA is short for exponential moving average. It's some sort of momentum, like it values more on the current batch of weights. And okay, when I'm using her image, I switched the model to the inference level. So this is experiment I run. And if you are just using the forward depth using 2, you can see this is pretty amazing for a neural network that's say like at this scale, but it can still reconstruct the things pretty well. You can see what this is doing. Let me explain. So I'm like, it's trying to, based on this 64 times 64 times like 1024 grid, like it has 64 by 64 grid. On each grid it has 1024 features. If you're like downsizing this image to 64 by 64 and upsizing, you will see it's just basically blur. That's you are trying to guess this 500 by 512 image by 64 times 64 times 3 channels. If you are using a 1024 channel, it's compressed. It has been compressed into this feature map. If you are trying to guess what the original image is based on the feature map, so the activation of this image and the original image can be closer and closer. This is what it looks like. You can see a lot of detail. It's very 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 impressive for these types of neural network. But like if you are like going deeper down, it also will be more distorted. But I do think like current one, it's like if you are doing it with content reconstruction, it's pretty nice. It is like for each feature, it does remember much wider stuff than other networks. It's like for many of the networks, they are pretty wide in feature numbers comparing to most of the other backbones. This is one thing. Of course, I don't know, like the thing I tried has bears any meaning, except like irritate my wife. But this thing, like I do want to talk, like I do hope this like there are following studies to continue this proceeds like on like how we want to do this switching state thing. This is so like before. This is like say the combining of this operation is basically the reverse of the decomposition, where we want to like what we always do when we want to reduce the size of things. Say if we have like an input size of this input channels, output channels, hidden size here. It all has parameter numbers like this. If you like if you like combining them, there will be this. So after combining, it will be much less, right? This is the basic logic sense of this paper, like what it promotes. But what if like you change the rank? Or like the hidden layer, or the hidden size, in some sense. If we like actually enlarge that, you can see if we double it to 1,000, you can see the after combined size is much less than the before combined size. And to notice like this is what ResNet do. Like if you are like running most of rest block, the hidden size is usually twice the size of input or output dimensions, right? The compressor can be much more impressive. I don't know if like in this paper they did not try to scale this thing to the double of its input or output size, but I do hope like if we there's a chance we can see that. Like I hope there are also studies it's about this aspect. So also if you like reverse it to this side, if you lower the rank or roll the hidden size, to do things like you can do pre-train steps with much lower rank with much less GPU or much faster training, and after a while like you can tone it up like to a much wider rank. So it's okay, you can train easy, you can pre-train easily, and afterwards, since this thing can simulate this thing or this thing can simulate like the direction both works. Like I don't know how people are going to perform this kind of action. So this is basically my understanding on this paper. It has lots of experiments. It's like of course I'm not going to run them one by one. They are impressive in some way, and I hope you can like this paper back. I hope you can like this paper better.